Last class we were discussing frequency shift keying modulation process. That is a time domain and the frequency domain representations. Okay. Now let me continue with the frequency shift keying generation. How to generate an FSK signal. Okay. Somebody is already muted. Okay. Anyway. Okay, ma'am. Can you see Neha?
Yes, sir.
Okay. Anyway, because of small disturbance. Okay. In FSK generation, we use frequency modulator. Okay. This frequency modulator is exactly similar to the frequency modulator which is used for generating analog FM. You know, analog FM we studied in the beginning of our course. Okay. So let me show the diagram. So this is the frequency modulator which we use for generating FSK. Okay. For this, what is the input? First input is binary input in polar format, and the next input is the carrier at a particular frequency. Okay. The next one, the frequency modulator will generate an FM signal. I mean frequency shift keyed signal, and it is filtered in a band pass filter in order to confine the bandwidth before transmit. Okay. Before the transmission, we need to confine the bandwidth of FM to a particular specific transmission band. Okay. So the output is FSK. Okay. Now let me show, and here one more thing. Let me explain. What happens here if the binary input is having high amplitude, higher level amplitude, which is representing 1. Okay, can produce a frequency, higher frequency. Okay, that means shifts the frequency of the carrier to high. Okay, the same way, if a binary input is low, negative level, the carrier will be shifted to low frequency. Okay, let me show the same pictorially. So this is a positive pulse input, which is representing bit 1. And this bit 1, which is representing in polar format as a positive pulse, will change the frequency to high value. Okay, you see? Let me show once again. Positive pulse and corresponding high frequency. Okay. Now, negative pulse. A negative pulse which is used to represent bit 0. That negative pulse will shift the frequency of the carrier to a low value, low frequency. Okay. Let me show once. See clearly a positive pulse, high frequency, negative pulse, low frequency. Positive pulse, high frequency, negative pulse, low frequency. Like that, the positive and negative pulses which are representing bits are changing the frequency to either high or low. So this is simply briefly about the generation of FSK signal. Now let me explain one more simple method. In that we are going to use two separate carrier generators, the carrier oscillators. Okay. So just like this. Here we have a 1 minute. Okay, here we have two carrier generators here, with the frequencies F1 and F2. And we also have a switch circuit. This switch circuit will switch either carrier generator 1 or carrier generator 2 to the output. Okay, isn't it? So that means if the binary input is high, the switch circuit will connect the upper carrier generator to the output. So the output is an FSK with the frequency of upper carrier generator, that is F1. If the switch is connected to second one, that is when negative pulse is given to the switch circuit, the switch will connect the lower carrier generator to output. So then output will be an FSK with the frequency equal to F2. Like that, these two carrier generators are connected to the output depending upon the value of the binary input, isn't it? Now let me illustrate the same function pictorially. Okay. So the switch circuit is having a connection. When a positive pulse is given, When a positive pulse is given, the switch is connected to the upper generator. So the output frequency is F1. Okay. Then if switch is connected, a negative pulse, negative binary pulse, the switch is closer to the lower one. So lower carrier generator is connected to the output. So output is an FSK with the frequency F2. Like that, it's very simple. See, the switch is toggling between these two depending upon the value of the pulses. Okay, isn't it? Very simple. Okay. Now, is it clear how to generate an FSK signal by using FM generator? Okay, that is a frequency modulator, or otherwise by using two carrier generators and a switch circuit. Okay. Now, let us know about detection. How an FSK signal can be detected, demodulated. Okay. There are two methods. One is a coherent method, another is non-coherent method. By using either of these two, we can detect or demodulate an FSK signal. Okay. So first, let us talk about the coherent detector. In this coherent detection method, we use two channels of coherent detectors. Did you get the point? Two channels of coherent detectors. Okay. And their outputs are compared in a comparator to decode that into either 1 or 0. Okay. Now let me show the diagram of coherent detector. You see, this is the coherent detection method used for detecting an FSK signal, which is having, look at here, see, here we have one channel, an upper channel of coherent detection and a lower channel of coherent detection and a comparator. Okay. See, the upper one is having a product modulator followed by an integrator. The lower coherent detection is having, but the upper product modulator is fed with a local coherent carrier, the frequency F1, and the lower product modulator is fed with a carrier having frequency F2. Okay, these two are coherent carriers. These two normally obtained from the incoming signal only. Okay, because to maintain the synchronous or coherency. Okay, now let me explain briefly. If the input signal is an FSK with the frequency F1, then what about the output of upper product modulator? You see, if input is F1 means it is cos 2 pi F1t, and here it is cos 2 pi F1t. So when these two are multiplied, the output will be having cos square, which can be represented as a sum and a high frequency term. So the output of this one will be some constant term and high frequency term. Okay, this constant term will be filtered by this integrator and the high frequency term will be removed by this integrator. So the output of this integrator will be having only a constant term, constant positive. Okay, now let us come to the lower product modulator. In this lower product modulator, the output of a lower product modulator is again the product of the inputs. One input is cos 2 pi f2 and another input is cos 2 pi f1. Okay, because we are talking about f1 only. Okay, so when these two are multiplied, output here is two cos terms having some frequency and a difference frequency, and these two are anyway will be removed by this integrator, because integrator is a low pass filter with very low cutoff frequency. So it will simply allow very low frequencies very near to zero, and all other frequencies will be removed by this integrator. So the output of this integrator will be zero, and output of the upper integrator will be some constant when input is F1. So when these two are compared by this comparator, the output will be a positive, and that positive value will be decoded into 1. Did you get the point? So if input is F1, here input of a non-inverting terminal of this comparator is positive, and here it is negative. So output is positive, and positive will be decoded into 1. On other hand, if input is an FSK carrying a frequency F2, then output of the lower product modulator will be constant plus high frequency term, whereas output of upper product modulator will be two frequencies. One is a sum and other is difference. Those two frequencies will be removed by this integrator, so output is 0, whereas output of this integrator is some constant. So this is constant, that is a positive constant, and this is 0, When these two are compared, the difference is negative. The difference, since it is negative, it is decoded into 0. This is how we can decode FSK. Let me show the entire scheme. Okay, let me illustrate the entire scheme pictorially. Okay, if input is FSK with F1, output of the upper one is constant plus higher frequency term, and the output of lower product modulator will be a low frequency and high frequency term. That means a difference term and some frequency, difference frequency and some frequency. Both will be now here. Output of this integrator no doubt will be some constant because high frequency will be removed by the integrator. Then what about output of this integrator? Both will be removed because both are actually well away, well far from 0. Okay, that's why output is 0. So when this is a positive, this is 0, the comparator will find out the difference. The difference is a positive difference because output is equal to this minus this input minus this input. Here the input is k, here the input is 0. K minus 0 is k only, positive k, some positive value, and it will be decoded into 1. Similarly, if input is an FSK with the F2, then what will happen? If it is F2, output of upper product modulator will be having 2 frequency terms. Okay, and the output of the lower product modulator will be having a constant term and a high frequency term. So output of upper integrator is 0, output of lower integrator is some constant. So here this is 0 and this is some positive constant. The output is this input minus this input. So 0 minus k, so output is minus k. When it is minus k, automatically output is 0. Okay. Okay, somebody raised a hand, but I'll clarify the doubt after finishing these slides. Okay, I'll give you 5 minutes. So this is how we can detect, demodulate an FSK signal. Okay, that means FSK with the frequency F1 is decoded into 1, FSK with 0 is decoded into 0. Okay. Now let us see non-coherent detector. So what do you know about the non-coherent detector? We already know something about non-coherence and non-coherent detectors. Non-coherent detector is nothing but an envelope detector, okay, which will detect only the envelope of a given input signal. But here in detection of FSK, how these non-coherent detectors are used? The same way coherent detector, here also we use 2 channels of non-coherent detectors. Okay, let me show the diagram. So we are using 2 channels. This is one channel of non-coherent detector. This is another channel of non-coherent detector. And this channel is having a band pass filter followed by an envelope detector. And this channel is also having a band pass filter followed by an envelope detector. Then what is the difference between these two means? The frequency to which the band pass filters are tuned. Here in this case, the upper band pass filter is tuned to F1, whereas in the lower non-coherent detector, the band pass filter is tuned to F2. Okay, then their outputs, the respective outputs are compared in a comparator, and decisions are made in favor of either 1 or 0. So let me give a simple example here. If input is an FSK with the F1, only the upper band pass filter will allow it, whereas a lower band pass filter will not allow. So the output of the lower band pass filter is 0, whereas the output of upper band pass filter is the same input. That is, if the input is cos 2 pi f1, the output is here also cos 2 pi AC. The amplitude is AC. AC cos 2 pi f1t. Okay. And what about the output of the envelope detector when input is AC cos 2 pi f1t? Output is only envelope. Envelope of cos term is how much? AC. So the output of the upper envelope detector is some positive value. It may be AC or some other value depending upon the amplitude. Okay. So the output of upper envelope detector is a positive value. Okay. Whereas the lower one, input of a lower envelope detector is how much? 0. So output is also 0. So here at the inputs of a comparator, one input, the positive input is having a positive value and negative input is having 0. So the difference is positive. So the positive is decoded into 1. On the other hand, if incoming FSK is having a frequency f2, the lower bandpass filter will allow f2. So output will be AC cos 2 pi f2 t, whereas the output of upper bandpass filter is 0. So output of upper envelope detector is 0 and output of lower envelope detector is non-zero. And when you find the difference, output is negative. So negative is decoded into 0. So like that, it will function. Now let me explain the entire scheme. No, with the waveforms. Okay, pictorially I can explain. If input is FSK with the frequency F1, then output will be output of the upper band pass filter is a carrier with the frequency F1, and output of a lower band pass filter is 0. Then output of upper envelope filter is constant because envelope of AC cos 2 pi f and t is AC. I'm treating that AC some constant. Okay. Here, output of lower envelope filter is 0. When 0 is subtracted from K, output is K only, and it will be decoded into 1. Okay. The same way, if FSK is having a frequency F2, output of upper band pass filter is 0, output of lower band pass filter is F2, and output of upper envelope filter is 0, whereas output of lower envelope filter is some constant. So when these two are compared, output is negative. When output is negative, it will be decoded into what? It will be decoded into 0, isn't it? So in this way, simply we can decode, detect and decode into ones and zeros an FSK signal. Okay, any doubt? Someone raised a hand. I don't see them. Now, if you want, you can ask before to move into the next topic, you know. So please raise your hand if anybody is willing to ask doubt. And while I was explaining in the middle, someone raised it. Neha, are you there?
There, no doubt, sir.
Okay, I think someone actually raised. I think they are. I think most of the people are simply joining and leaving. They are not turning attention. Pavani? Pavani, if you try to.
Sir, I'm here, sir.
Pavani?
Sir,
Are you listening?
yes, sir.
Okay, ma'am. Do you have any doubts?
No, sir.
Okay. I think someone raised a hand, ma'am. Otherwise, I'll move on to the next one. Okay.
Oh, no, sir.
Okay. Can I proceed?
Yes, sir.
Okay, ma'am. Now I'll proceed with the. So assuming that no one is having doubts, I'm proceeding. And anyway, I'll send all the slides as well as some PDF copy on ASK, PSK, and FSK. I think almost with this FSK is over. Okay, that means ASK and PSK already covered, and with the today's class, FSK is also over. Okay, and theory regarding to all of these modulation schemes is well given in PDF form. I am going to submit the same, and somebody is there in charge. Okay, ask Manasavina. I think Manasavina, let me unmute. Manasavina, where are you? And you better come, ma'am. Manasavina, you unmute.
It's not.
Okay, ma'am. Unmuted.
Hello?
Manasavina, are you there?
Yes,
Okay,
sir.
ma'am. Ask me.
Yes,
Ask me.
sir.
Ask me.
Sir, actually, non-current detector, the BF, after bandpass filter, the F1 is came, then down it is 0, na sir. Why it
Yes.
came 0?
Oh, okay. I'm giving because the band pass filter is tuned to F. Upper band pass filter is tuned to F1, you know. The lower S.
Yes, sir.
Lower
Yes, sir.
band pass filter is tuned to F2.
Yes, sir.
So when band pass filter is tuned to F2, and for the same band pass filter input is a carrier with F1, how that carrier will be allowed through band pass filter? Because band pass filter is tuned to F2. No. What do you mean band pass filter?
Yes, sir.
Band pass filter is a filter which allow a small band of frequencies. Small band
Yes.
of frequencies
Yes, sir.
around F2. Around F2.
F2.
Okay. F2. But the input
Okay,
is
sir.
input is F1. You know. That's why F1 actually
Yes, sir.
cannot pass through a band pass filter which is tuned to F2. So the output of the band pass filter which is tuned to F2 will be 0 only. Okay. This is
Okay,
for
sir.
this is for an FSK carrying frequency F1. అంటే FSK సిగ్నల్ ఫ్రీక్వెన్సీ F1 అయినప్పుడు అప్పర్ బ్యాండ్ పాస్ ఫిల్టర్ F1 కి ట్యూన్ అవుతుంది కాబట్టి ఆ బ్యాండ్ పాస్ ఫిల్టర్ కూడా అలో అవుతుంది. కానీ లోయర్ బ్యాండ్ పాస్ ఫిల్టర్ కూడా అలో కాదు, ఎందుకంటే అది F2 కి ట్యూన్ అయి ఉంటుంది కాబట్టి. ఓకే, కాబట్టి లోయర్ బ్యాండ్ పాస్ ఫిల్టర్ అవుట్పుట్ ఏమవుతుంది? 0 అవుతుంది. అప్పర్ బ్యాండ్ పాస్ ఫిల్టర్ అవుట్పుట్ ఏమవుతుంది? అంటే ఐ మీన్ క్యారియర్ విత్ F1 అవుతుంది. క్యారియర్ F1 అయినప్పుడు దానికి యాంప్లిట్యూడ్ ఉంటుంది కదా, యాంప్లిట్యూడ్ ఉంటుంది కదా, ఏసీ ఉంటుంది కదా. సో కాబట్టి ఏసీ కాస్ 2πf1 అనేది ఎన్వలప్ డిటెక్టర్ కూడా మనం పాస్ చేసినప్పుడు అవుట్పుట్ వచ్చి ఎన్వలప్ ఉంటుంది. ఎన్వలప్ అంటే ఏంటి? ఏసీ కదా. సో కాబట్టి సమ్ పాజిటివ్ వాల్యూ అంటే F1. కాబట్టి ఇన్పుట్ FSK F1 అయినప్పుడు అవుట్పుట్ అప్పర్ ఛానల్ అవుట్పుట్ మాత్రము పాజిటివ్ అవుతుంది, లోవర్ ఛానల్ అవుట్పుట్ వచ్చి 0 అవుతుంది. కాబట్టి ఏమిటి? రెండు కంపేర్ అయినప్పుడు అవుట్పుట్ వచ్చి పాజిటివ్, రెండు కంపేర్ అయినప్పుడు అవుట్పుట్ పాజిటివ్ అవుతుంది. సో కాబట్టి 1 గా డికోడ్ అవుతుంది. సేమ్ ఎగ్జాక్ట్ గా రివర్స్ అనమాట. వెన్ FSK అనేది F2 క్యారీ చేస్తుంది అనుకో, F2 క్యారీ చేసినప్పుడు లోయర్ ప్రోడక్ట్ బ్యాండ్ పాస్ ఫిల్టర్ అవుట్పుట్ ఏంటి? నాన్ జీరో అంటే ఏంటి? F2 అవుతుంది. సో దాని కరస్పాండింగ్ ఎన్వలప్ డిటెక్టర్ అవుట్పుట్ ఏమవుతుంది? 1 అవుతుంది, ఐ మీన్ పాజిటివ్ అవుతుంది. సో అవుట్పుట్ ఏమవుతుంది? కంపేర్ చేసినప్పుడు నెగిటివ్ అవుతుంది. సో నెగిటివ్ కాబట్టి జీరోకి డికోడ్ అవుతుంది. ఓకే, ఇస్ ఇట్ క్లియర్? Okay, sir. Okay, now let me continue. I have only 10 minutes to finish it. Okay. Now I'm going to share. I'm going to share. Now let me continue. So with this, almost all digital modulation schemes like ASK, PSK, FSK, the modulation processes both in time and frequency domains, and generation and detections all were covered. Okay. Anyway, I'm going to send all the copies regarding to this, okay, including this presentation. Okay. Now, let me continue with a performance of digital communication systems. Okay. So what do you mean performance in the first place? Performance means how effectively a communication system, okay, how effectively a communication system works against noise. So when you compare with the noise, how effectively a communication system is working, that actually tells about the performance. If the performance is good, means that particular communication system is working against well with respect to noise. Okay, is it? Now, that's why many of the times the performance is also referred to as noise performance. Okay, noise performance. Okay, okay. Now, how this performance is measured? Because if the performance is not measured, it is no use. Because with the after knowing the performance, we can easily compare any one system with the other communication system, whether it is analog or digital. That's why we should be in a position to measure the performance. Okay, how to measure the performance? That actually varies from type of communication system to another type of communication system, whether it is analog communication system or a digital communication system. So in case of analog communication system, what happens? The performance, noise performance is measured in terms of figure of merit between input and output SNRs. Okay, by comparing input and output SNRs, we can have a figure of merit. With the help of the figure of merit, we can measure the performance. This is how we measure the noise effect in analog communication systems. But in digital communication systems, we cannot do the same. We follow other way. In digital communication system, how you measure the performance means we measure the performance with the help of error probability. Okay, what do you mean this error probability? Error probability is the probability of receiving any transmitted bit in error. Okay, did you get the point? The probability of any transmitted bit received in error. For example, if 0 is transmitted, how much is the probability of 0 to be received as 1? On the other hand, if 1 is transmitted, how much is the probability of 1 to be, to receive it as 0? Okay, so if 0 is transmitted, how much is the probability to get it as 1? 1 is transmitted, how much is the probability of 1 to get it as 0? This is called error probability. That means we need to find out these probabilities. Okay, so with the help of these error probabilities, we can measure the performance. So if error probability is higher, the performance is noise performance. I'm calling it as noise performance. Higher the error probability, lower the noise performance. Okay, so this is what we need to find out. First, we need to find out an expression for this error probability. Okay, normally error probability is expressed in terms of Q function. Okay, some Q function. Okay, and we'll discuss it in the next few classes about this error probability. Okay, so after finding error probability, this is general expression. After finding error probability expression, we can apply this error probability expression to find out error probabilities of different communication systems or modulation schemes like ASK, PSK, and FSK. Okay, for all these, you need to find out error probability. Error probability. Some of these may have better error probability. Some of these may have worst error probability. Based on that, we can compare one system with the other system, and we can comment whether which one is best, which one is poor, which one is weak like that, which one is strong like that. Okay, all these performances with respect to noise only. When you're talking about the performance of a system, you're talking about how effectively that system is working, acting with respect to noise. Okay. Now, if you have any doubt, you can ask. I'll continue. Otherwise, I'll continue. If you have any doubt, ask me. Chari? Chari voice is not audible. Okay, two participant raised. Let me see. Okay, who raised the hand, ma? Uh, Again, Manasavina and Chari. Okay, first let me give chance to Chari.
Sure,
Chari,
sir.
you raised your hand.
Silence,
Okay, you
silence,
have
sir.
it.
You
Okay. You responded
no
to
doubt,
me.
sir. You ask me.
Okay. Then I'll come to Manasavina again. Manasavina.
Sir, actually, last time I have raised the hand, that only you have seen now, sir.
Okay, man. Okay, fine. Then anybody is having doubts? Chari, are you following the attendance?
Yes, sir.
Okay. Anyway, because I'm concentrating on presentation, so you better follow the attendance. Okay. And